Are you alive, guys? Still surviving? Since there is a step, for installing the packages, it takes some time. So we will just open the notebook and do this step first, so that then we can come back to it. I will introduce the topic in the meantime, and then you have the packages already installed. Okay. So are you in this page, in the GitHub page? You can go to the resources again, and then the GitHub link. And then you can open Google Colab. And then there is only one file called clustering. So this time it cannot be wrong. It's no bacteria, nothing. Just click it here or here, it will open in another pop-up. You can see I just updated a few seconds ago. It's important, as we said, that we create a copy. And you can rename these as you want. Are you all here? Yeah? So in the first step is just to check for the time of the last update. As you can see here on the right, is connecting to the runtime. So now it's ready. And this is the time-consuming step. So just click on the packages, and now we'll install the packages. Okay? Yeah. So I will introduce the topic now, and then we come back to this. Okay? So I would like to introduce some concept related to clustering and heat maps. I know that for many of you would be trivial, for some others would be a new thing. It's a heterogeneous audience, so we have to try to fit a lot of things inside. And during this summer school, probably you heard a lot of terms. Many of them can be under this umbrella of machine learning world, we can say. We can divide machine learning in two sides. So one supervised branch and one unsupervised branch. And the supervised branch basically uses a label to classify, in this case, socks, if you want to classify socks by color, or predict a number like the length of the ties, for instance. And the part that we are talking about today, actually, Madeleine already mentioned it a bit, is dimensionality reduction. Termanova PicoAce is one of those, PCA is one of those, and many others that you heard before, Disney, UMAP. And there are methods based on association, so how frequent you can find an object together with another one. And you can also find the clustering branch here, that is the one that I'm talking about today. So we want to put, for instance, similar clothing together. The supervised learning, the labels are provided, as I said. You have your data, and you divide your data in training and testing. You build a model, machine learning model based on the training. Here we have a lot of type of fruits. And then we build whatever machine learning we want, and we build a predictive model on this. The test set is never seen by the model and is used to evaluate the performance of your model. This is a very generalization, of course. There are many more complicated ways of doing this. These are just some examples, like random forest probably is the most common used in metabolomics, I think, together with some others. Linear regression, logistic regression, boosting models, and so on. But today I want to focus a lot on unsupervised learning. So no labels are provided. In this case, we have a bunch of animals, and we want to build a model that will group together objects, observations that are very similar to each other. So here we have the original cluster data, and here we have cluster data. So many observations close to each other would be very similar in the grouping. And the only clustering approach I'm talking about today is hierarchical structure clustering, where basically the goal is to estimate the relation between every sample or feature in a dataset. And it can be visualized in this very nice way with a dendrogram that you probably saw many times before, where the height here indicates the cluster distance. So from the bottom up, you have more similar objects until the top. And for instance, here we can split cats and dogs and the size and so on. There are many ways of doing it. The most popular is called agglomerative hierarchical clustering, where you have an iterative process where at the beginning, every observation is a cluster. So every sample, let's say, is a cluster. And then in our iterative process, step by step, we merge the clusters close to each other according to their similarities until this process stops when you have one large cluster. And how we merge the clusters using this linkage method. So you can do it in 4 different ways. You can calculate the distance between 2 clusters that is minimum, or the maximum distance, or the average, or the centroid distance. So in this case, let's say the centroid is the center of the cluster. What we are interested in is to find clusters, right? And a priori, we don't have defined number of clusters when we have a dendrogram after hierarchical clustering. So we want to cut the branches of this tree at a certain height where it's for us meaningful. And this is quite challenging because it can be quite dependent on your field, the samples that you have, the visual inspection that you do in your data, but can also be computationally calculated. And I will show you in a moment. So here, this dash line indicates where I cut the tree, and all the branches below are the clusters that we form. There are different ways of cutting the trees. One of the simplest methods is called elbow method, where the within clusters sum of distances is calculated every time a cluster is merged together. And you can plot this, and where you observe in this curve a bend, a knee, some people call it, or an elbow, is the proper amount of clusters. There are pros and cons of hierarchical clustering. The pros is that it doesn't need a defined cluster. You can just plot the dendrogram and expect the data. But can also be very challenging to define a cut in the dendrogram if you are interested in defining the number of clusters. Probably you're also very used to heat map concept. Heat map is just a visualization of your data. You have samples here, index, and features in the columns, and the color is just the intensity of your values. In our case, the intensities of the metabolites. Here you can see an heat map before doing hierarchical clustering, so there is no order here. And here on the right, you can see after hierarchical clustering. As you can see, the rows and the columns are reordered according to the most similar objects or observations. And we can define the number of clusters in the heat map itself by cutting the tree, as I showed before. And here you can see 3 main clusters according to the samples, and 3 main clusters according to the features. Okay, so let's come back to the notebook. Let me know if there is anything unclear, of course. Yeah. My strategy didn't work. I hope that coming back here, you could have fixed it.
Maybe you have other questions in the meantime?
So the clustering, you build a dendrogram first, and then plot it for basically.
Yeah.
But at least in phylogenetics, there are many different ways to build those dendrograms.
Yeah.
Sometimes get quite different results. That must be the case with this stuff as well.
Yes. So even when we run the code, actually every time is there is some sort of stochasticity. So every time you generate, it could be different according to the complexity of the data set. So that's why we fix usually a specific point in the code that we will show, and then you say I want reproducible results. So every time you will generate, it will be the same result. But there are different ways of cutting the tree. It's true. In phylogeny, you use PGA or something like that. I think something, I don't remember. Yeah, some different ways. And hierarchical clustering is just one of the most basic way of doing clustering. There are many others like k-means or density clustering and so on that are more advanced. But it's the easiest to explain, I think, from the pedagogical point of view, because as a visual representation of your samples. And it can become very difficult to interpret when you have 2,000, 3,000 samples, of course. Or if you plot the features, then it would be 5,000 features, and every line in the tree is a feature.
In the end, the question is it meaningful clustering?
Yeah, to do that, and there are some comments here, you have to check for the stability of the clusters. So there are methods that shuffle around the labels, for instance, of the samples, and verify if your clustering was robust or not. In that case, you can refuse the clusters or not. And we need an elevator song here. Yeah, it could be. Yeah. Yours done? Okay. Depends on the net. Of course, you can go for coffee or whatever, huh? Instead of inside. Yeah. Now we will upload our files. Yeah. Yeah, mine is done, but I don't know the others. So it's the same files of the entire day, basically. So the feature table, the imputed quant table, and the metadata, okay? The imputed quantification table?
It's the exact same input.
Yeah, the same input as a PQA.
Yes.
Are you all in? Okay, we wait. Did you install the libraries? It's still ongoing. Libraries are done? Nice. Does it work? Yeah? Yeah? Install, all of you? Yeah? So I'm moving on, okay? So first we load the libraries. This time should be fast. And then here you can just copy and paste the path of your files as before, if you remember. You can just do like that and copy the path. Yeah. And then you can put it here. One for the feature table and one for the metadata file. Then we will read the data and we'll check the dimension of our files. We can visualize, as you know already, the first 6 lines of our feature table and the first 6 lines of the metadata. Did you manage to read the files? Yeah?
Anyone have issues?
No issues, okay. Good, wow, that's the first time. This is just to check what are the attributes of our metadata, the attribute sample. As you can see, we have one paper blank still. And this is to check how many of the samples in the metadata are in the feature table. As you can see, one is not and is the paper blank. So we are gonna check this. And you can see the paper blank here. We want to remove this from the metadata. And we check the dimension again. So you should have 12 samples, right? And 3 columns. We transpose the feature table because we want the features in the columns in our analysis. And we check again. Yeah? You check again the dimension if you want. And it should be like 12 samples and a specific amount of features. We check if the rows are in the same order. At the beginning, they are not, but we transform them to be in the same order. We scale the data. All these steps are the same on the PQA if you have a deja vu. And then we check again. So here it starts the actual clustering. I reported here again the steps, but we don't need to go through that again. There are different ways of doing it. There are different distance matrices, as Madeleine already mentioned. Here we will go with Euclidean, but you can change it with Canberra. You can play around with it. And I reported also where you can find all the distances that you can put. So we calculate first the distance, the pairwise distance between all the samples, the features and samples. And here we calculate the hierarchical clustering. As I mentioned to you before, here we set this seed that is just a way to reproduce the analysis always in the same way. If you don't put this, then result can change because it's stochastic. And this is just one of the methods that I mentioned, the linkage method. It can be complete, it can be average, it can be centroid. Yeah.
So if you want to do like similar to bootstrapping,
yeah,
you would do 100
yes,
branches with different
exactly, yeah, and shuffling the labels as well. So yeah. Then we plot. And I'm curious to see if you get something similar or something completely out of the blue. So what I get is that the samples 45M cluster in a way together in this split. I don't know if you get something similar. And then there is a second split here, major split. And in this major split, we have some 2 subclusters, we can call them. The 15 here, and the M and the 5M. You get something similar? Good, reproducible, we can publish. Next, it seems here that there are two main groups, but it seems there are other two subclusters. So we want to cut the tree, and in this case, this parameter indicates how many splits we want. So in this case, I say 3, and we can check the result, which samples belong to which cluster. Is it clear? And you can check how many samples are in each cluster. Then we can also highlight with the colorful rectangles the clusters if you want to use it for publication or anything else, as you can see here. And you can also color the branches if you like. As I said, it can be tricky to define the number of clusters. Now I say 3, but we don't really know very well at the moment. Therefore, we will proceed with this elbow method that I mentioned in the presentation. Let's run this. And we can see this bend, this knee here, or elbow at 3. So it could be that there are 3 clusters. But the elbow method is a bit sometimes ambiguous. It can be 2 or it can be 3. Therefore, we will perform another analysis that is called silhouette method, and we will check how many clusters suggests. In this case, it says 2, because there are 2 main splits actually. You get something similar? Yeah. Another thing that it could be altering your analysis in the clustering if you get something completely different is the input data. Sometimes metabolomics data are very noisy. We impute a lot and we create this zero variance problem. So imagine 0, 0, 0, 0, and one feature that has a value. So let's see what happens if we remove those features.
Sorry, can you go up?
Yes. It's different. How many clusters suggests?
1, 2, 3.
3 clusters. And the elbow method as well?
Yeah.
Oh, that's nice. They agree.
So what if your clustering suggestion is your tree is clearly wrong?
Yeah.
Clearly wrong sounds a bit weird, but the PCA gave the clustering as I would expect.
Yes. Yeah, exactly. Because the interpretation from the hierarchical clustering, it's not 100% what you expect as a cluster. It's more a visual interpretation of the hierarchical relationship of the groups. So I will use more advanced methods like k-means or density clustering to discover more meaningful clusters. But also, as I wanted to mention here, sometimes it could be because you have this zero variance problem. And then when you cluster, you obtain things that are unexpected. So I wanted to show you what happens if we remove those. In this case, I don't want features that have a 0 median absolute deviation. Let's say variance. You can change this as bar, it's the same. Remove this. And we check the dimension. In my case, I don't remove the many features, but I heard that some people have 50,000 features. So maybe you will reduce a lot your dimensionality. It happens to you? Do you remove a lot or very few features? Very few, okay. So if we generate again the clustering, for me, it doesn't change. So I can conclude from here that the samples here, M and 5M, actually are quite close. And they make sense because in the dilution process, they are also close in time. So we excluded that this clustering is biased by the fact that there are many noisy features. Finally, we want to generate the heat maps. We check again the attributes that we have. And we prepare here our input data for the heat map. And then we plot. Do you get something like that? Something very different or something very similar? Somewhat different? Which difference do you see in yours? Okay. Yeah, this one could be just when you plot, but you can check how the hierarchical clustering is to see if it makes sense. Because it could be, because also again, it starts from a random point. And as I said, we can perform a clustering to break in pieces, in blocks, these groups. We can cut these trees to obtain clusters. And you obtain this nice visualization where you have a clear cut of the groups. As you can see. But I want to underline that this is what I observe in my dataset, but you can play around, of course, with the parameters and say, I don't want 3, I want 4, or my elbows or silhouette approach suggests 4 clusters or 3 clusters, of course. Yes.
Can you repeat where to change the number of clusters?
Yes. In this last part or before? In this last part, you can change it here for the rows, and this is for the columns. And here, this is a way to extract the features that belong to a specific cluster, because I think you can use it in the future. If you want to combine your results from GMPS or series of any other annotation system. So I want to check how many features I have in each cluster. And then I just extract them from this object. What you should be able to see at the end of doing this is a table with the features and the cluster assignment. Is working? Nice. And then you can write the file. And that's it. Basically, you can save the PDF and go maybe in Illustrator and modify it or whatever you want. And it's important that you download these files because they will disappear once you close. So remember to download the feature clusters and the ITMA. It's working. You can open it and see how is the result.
Get stuck in one of the
One of the things. Someone else has problems?
Just
Yeah.
So if you want to publish a paper where you use this, like, would you then share, or like the question is a lot of details, would you then share
Another book or?
the notebook with the
I will share.
publication, or-
I will share everything. So from the notebook to the PDF files, if you want to include them in the paper. Otherwise, just the notebook that you generated, you will remember all the plots and all the other commands that you've done. I usually will share it as a notebook, or it's nice also as a HTML file or PDF. So then people can just open it without need of knowing Google Colab or Anaconda or anything else. You can download it as a HTML file. Yeah.
The journals that require that you.
Nowadays, journals require to release the code in most of the journals. So you really need to think about how reproducible are your results, I guess. And I will share also my content environment if I was working my computer so that people can install my environment as well. So it's exactly the same. Actually, at the end of this notebook, you can see here that I'm saying I want to see all the versions and all the stuff that I'm running. So here you can see I run in Ubuntu because Google has Ubuntu, and there's R version 4.2.1 and all the versions of the packages. And in the paper, you have to refer to all the versions that you run, because many times you get different results. R is an open source software that is given without guarantee that it works. So. Okay, where?
I have an error because of my
Input data. Okay.
something that I'm not getting.
Okay. Yeah, of course. You work for you guys? Yeah? Nice.
Well, it works, but I'm not happy with my clustering.
I know, really. Can I see it?